analog lab. I'm going to start this lab just by saying this is going to be the last week that you're going to have a lesson. Starting next week, we will be working on final projects. So I'm going to talk more about that at the end of this lab. So the format moving forward will be every week I'll still release a video, and it's going to be just sort of helpful information related to analog electronics. But when we meet in office hours, we will be talking about your final project, and I would like you to make progress every week on your final project that we can talk about. So this is your last official homework assignment for the class, and beginning next week, we will be doing final project progress reports. So I'll talk about that at the end. This particular lab is one of my favorites. This is going to be about distortion. And before we talk about distortion, we're going to talk a little bit about diodes. So I'm going to swap over to my desk camera. And you'll notice I kind of took everything off the breadboard. The only thing I have is my input and my output. So we'll be listening to some distortion circuits. I've got my scope here, but it's not plugged in yet. And basically, what I've got here are a couple of diodes. And so you may recognize the word diode as it is part of the acronym LED, a light-emitting diode. Basically, a light-emitting diode lets current flow in one direction. And when you put current in one direction, the light lights up. If you try and hook it up backwards, it doesn't light up. So thinking about that a little bit, the diode is basically the part of the LED that doesn't light up. So it's the part that lets electricity flow in one direction and not the other. If you can see up close, this diode has a silver band on one side. That is the minus part of the diode. This is the part that would go to ground, and the other part is the positive part. And if you notice, both of these legs are the same length, so it doesn't abide by the same rules as the LED. But we're going to use this stripe to indicate that this is the negative side of the diode. So I'm going to put this down, and let's talk a little bit of theory before we actually dive in. So here is what a diode looks like. I called them the positive and the negative legs, but officially they are known as the anode and the cathode. The cathode is the negative leg of the diode, the anode is the positive leg, and this applies to the LED as well. So it is a polarized component. The silver band is the cathode, the negative part. And if you think about it, like the silver band looks like a negative sign, kind of. You can remember it that way. So what we're going to do is we are going to use diodes to create a clipping circuit. Clipping in audio you may be familiar with. If you've ever cranked up the volume so loud that it sounds distorted, it is because you stretched your audio wave past the point that your speakers can handle it, and so you hear a distorted signal. Well, what we're going to do is we're going to force that clipping to happen at a much lower voltage using these diodes. And if anyone plays guitar, you are probably familiar with a distortion pedal. Diode clipping is only one of the ways to create distortion. And so we can use this extremely simple circuit to create distortion, fuzz, overdrive, all of the different varieties of distortion that exist. So first, let's look at something here. We're going to do a quick test using one battery, one resistor, and one diode. So I am going to use a 1K resistor and my diode and one battery. I'm going to still use my same battery harness, but I'm just going to leave the -9 unconnected. So let's build this really quick. so I'm going to grab my battery harness. I actually disconnected it from the breadboard, but it is right here. And I'm going to leave it all connected, but I'm going to take my power and plug it into the red. And I'm going to take my ground and plug it into the ground. I'm going to leave the other side unconnected. So then I'm going to take my 1K resistor. I'm going to go into the positive rail and into the breadboard somewhere. Then I'm going to take my diode and I'm going to plug the anode, the positive leg, into the same row as the resistor. And the cathode is going to go into ground, right? Super simple circuit. I could actually zoom in a little bit because we're not using much real estate here. So basically, 9 volts, resistor, diode, ground. That's it. So now what we're going to do is we're going to get a multimeter and we're going to record the voltage across this diode. Okay? So let me do that, and I want to see what we get here. I'm going to actually plug my batteries in. And actually I only need one, so I'm only using one side of my connector. And I'm going to take my multimeter, I'm going to set it to my DC volt setting. Let's put it over here so we can see it. Bump it over a little bit. Okay. And we're going to go across this diode, and let's see what we get. So I'm looking at about 0.69 volts going across this diode. All right, so let's just jot that down. So 0.69 volts. That's our first reading. So now I'm going to replace the resistor with a 10K and then a 100K, and we're going to keep recording the voltage. Now, if this were to work as a resistor, what should happen? So if this were a resistor, I should basically see the voltage decrease, right? Because I'm increasing the other resistor, so that resistor should technically consume more volts as I keep this one the same. But let's see what happens. So I'm going to pop this 1K out and pop in a 10K. Same idea, it's going to go from +9 to the diode, same exact circuit, and let's see what we get. Focus. All right. So now with a 10K, 0.58 roughly, 0.59. Okay, so it did decrease. Let's see with a 100K. I'll pop this out. Get my 100K. Pop that in. Okay. And let's see what we read here. .4748. So we've basically increased the resistor by an order of magnitude each time. And the voltage change is about 0.1 volts, which basically means, you know, the voltage across the diode isn't changing that much. No matter what resistor I put in there, I'm still kind of seeing the same kind of voltage drop across the diode. So, you know, the diodes have, they have a different kind of reaction to voltage than a resistor. They're not going to work as a resistor, as like a resistor divider does. And so this is important because when we put them in our circuits, they're only going to consume like 0.4 to 0.6 of a volt, and it's going to be pretty consistent no matter what our voltage divider is. So let's try this with AC. We're going to take our battery out, and we're going to run an audio signal through this circuit. So I don't need my battery anymore. But I'm going to change this back to a 1K. And rather than plug this into the power rail, I'm going to just plug it into my audio jack. So here's my 1K. I put this back in. I could actually unplug this battery. I don't need it anymore. And I'm just going to unplug this whole harness because we're going to look at this as a passive circuit. And then I'm just going to take a wire and go from my DC blocking circuit up here through my diode. And I'm going to look at this on an oscilloscope. So I'm going to plug my oscilloscope in here, ground, and the output is actually at this point between the resistor and the diode, right? Because if I went after the diode, I'd just be looking at ground, and we're not going to see anything at the ground. So we're going to look at this wave right here where the resistor and the diode meet. So audio coming in here, there's my jack, DC blocking, and here is where my scope is reading. So now I'm going to move this over. And let's take a look at what's going to happen on the scope. And I'll lift this up a little bit so we can see. All right, so let's go back here. So this is the circuit again. I'm going to play a sine wave through here, and we're just going to take a look at what happens. Okay. All right, so let's get into somewhere where I can see the wave. All right, now let me just turn this up and make sure I can see it. Cool. All right, got a sine wave. So basically, you know, I can turn the volume of my computer up and down, and this is pretty normal, right? So let me see if I can get this any louder. So I think. There we go. All right, so I'm actually going to bypass my DC blocking circuit here, just so I can show you what's happening. So I'm going to just come right out of the audio jack. Let's not use a DC blocking circuit for right now. And I'm going to actually look at this on a smaller scale, just so I can show you this. So I'm going to look at this as the 0.1 volt scale, right? Let me actually go to 1. I'll divide this by 2. So I'm looking at this. Yeah, okay. 0.1 here, x2 here. So basically every division is 0.2. And what I want to show you, I'm just using my laptop volume. As I turn this up, I want you to look at what happens to the wave. And actually, maybe I'll flip this down so you can kind of see it a little better. As I increase the volume, the top half of the wave kind of gets chopped, right? Do you see that? So now I'm on 0.1 and x5. So all of these divisions are 0.5. So basically, I have a sine wave, but as I increase the volume, when it hits like the first line, it starts to like kind of flatten out, right? And as I increase the volume, that kind of flat line remains at about the same level, even as the volume goes up, right? So what's happening? So basically, let's go back to our lab. The first time we plugged in this diode with our battery, we measured the voltage, and we got something like around 0.5, excuse me, 0.6 volts. What that means is the diode has what's called an on voltage. It's the voltage that it needs to exceed in order to kind of activate. And so what we did was we said, okay, let's send an audio wave through this diode. Well, we know that somewhere around 0.5, 0.6 volts, the diode's going to turn on, and it's going to be connected to ground, right? So this wave that I'm sending through here, all of the audio that is less than 0.5 volts will pass to our output. Anything greater than that is going to pass to ground. We're going to chop it off. But we only chopped off the positive part of the wave, right? If you look back at our oscilloscope, the negative side is unaffected. That's because this diode is only passing the positive parts of the wave to ground. This is called an asymmetrical clipping circuit, right? The title of this is Asymmetrical Clipping. This will sound kind of weird. Let's see what this sounds with music. So I'm actually going to, we'll run some music through here, and then we'll see what happens. So I'm going to go from the same location into my output here, and let's play, and we'll see what this sounds like. Nope, I should turn off my... So we might need to amplify this before we're actually going to hear it, because as you can see, I'm not getting anything above 0.5, really. And this is really kind of the problem with distortion, right? Is you can see what's happening on the sine wave, but we're not going to actually hear it until we amplify it. So what I'm going to do is I'll build a quick amplifier circuit, and then we can listen to it. So actually, before we do this, let's talk about symmetrical clipping. I want to do that at the end. All right, so let's go back. So what I want you to do is I want you to look at a sine wave on your oscilloscope, make sure it's working, you're turning the volume up and down, you're seeing the sine wave grow. Then I want you to plug it into your diode, and I want you to take a video of you turning your laptop volume all the way up and back, and I want you to see the clipping. You might have to adjust the sensitivity on your oscilloscope so you could see it clearly happening. The settings that worked for me were 0.1 volts on sensitivity 1 and X5 on sensitivity 2. So basically, I have each horizontal line as a 0.5 volts, and you should be able to see a very clear clipping line happen. explain what you see and how it relates to the DC circuit in part 2, right? I did explain this, so let me know again what is happening. Okay, so let's try symmetrical clipping. Actually, let's listen to it first, because I want to listen to the difference between symmetrical and asymmetrical. So, let's go back here. So, let's do this. I'm going to pop this out, and we're going to put my DC blocking circuit back. And if we can amplify it, it should be able to work at a much lower volume, because we can crank the gain through our op-amp. Okay, so I've got an op-amp here. And I'm going to get my battery harness. And we'll just plug it kind of directly in, because I don't really need much else here. Okay. I'm going to put my 10K to ground, because that helps me with my non-inverting amp. Okay. Then we're going to go into pin 3 with my audio signal. And what I'm actually going to do here is, let's just look at this circuit really quick. Open up a new tab. I'm just going to put in a gain of, let's do like a gain of 10, just so I can see something. I'm not going to use a pot. I just want to make it a hard gain of 10. And we could swap this out and listen to how that changes the distortion. So take a look at this, just in case we forget how to build it. We can go back to week 5, and we'll use our non-inverting op-amp, right? So we're going to use, let's use a 100K for R2, and then a 10K for R1. And so we'll put this 100K in between pins 1 and 2. And then I've got a 10K here going from pin 2 to ground. And now I will go from the output into my distortion circuit, which I left right here. And I'm going to pop my batteries in, because I've got a op-amp in here now. I need to power it. All right, so let's see if this sounds any different. Oh, I've got some radio stuff going on here. Interesting, interesting. Let's see if we can figure that out. All right, so let's take a look. So we've got something weird going on here. Let's see if we can figure it out. Yeah, we're going to pin 3. All right. Let's try this one more time. just going to see with my output here if I'm hearing anything coming in. Okay. So let's see, we're not getting anything into this resistor maybe. This might be an issue with my audio jack, perhaps. Cool, okay. And then in here, anything? All right, so now, distortion. So basically, I think my capacitor was not connected entirely, but I'm going to A/B test like the clean versus the distorted signal just by moving this output wire. So this is plugged into the distortion right now. Clean. So this is all distortion is, right? We're simply sending this amplified signal through this diode, right? And I just built a quick non-inverting amp right here with a gain of 10 just so I could hear it more clearly. Now, if you're doing this for your final project, you might find that a gain of 10 isn't quite enough. If you want this to sound more distorted, you can increase this gain. You can have two amps back to back where one amplifies it. You can have an amplifier after the distortion circuit. So if you wanted to make the distorted signal louder, you can have an amplifier on the other side. So this is asymmetrical distortion. Let's go back and look at symmetrical distortion. So basically, as you might imagine, we put a diode from our signal to ground. That's going to ground all of the positive voltage above 0.5, 0.6. If we put another diode in the opposite direction, you can probably guess that this is going to ground the negative waves. So let's do that. Let's see what happens. So I'm just going to take a second diode, and I'm going to connect it into the same rows as my first diode, but backwards. So the cathode, the negative part, is actually now facing my signal path, right? So let me do a quick test with a sine wave first. Let's see what this looks like. We don't need to listen to that. Let's unplug that. So, check out my oscilloscope. There's my wave, right? As I increase it, I'm chopping now both the positive and the negative sides of the wave. So I get almost like a square wave, right, as I increase the volume. I'm clipping both sides. This is as loud as I can get. And I've pretty much turned this sine wave into a square wave. Let me stop this, and we'll put pulp back on, and we'll see how this sounds with actual music. If you take a look at this wave, you can see that it's only occupying this space between positive 0.5 and negative 0.5, right? No matter what, this wave will not get bigger than those two voltages. That's not what I wanted. Thanks, Bluetooth. Let's turn Bluetooth off so that doesn't happen again. Okay, so now what I'm curious about is if I change the gain on this op-amp, what will this sound like, right? So we have a gain of 10. What if I did a gain of 100? If I get a 1 meg resistor, so let me just make sure I can still, all right. So there's pulp with a gain of 10. Let's pop out this 100K, and I'm going to pop in this 1 meg. So this is now a gain of 100. So I'll swap it to the clean. Here's clean. And distorted. So, it's a lot of exciting stuff we can do here. Let's go back to the lab. So basically, you can test this with music if you want. It's not required. If you don't want to build the non-inverting amp, you can look at everything just with the sine wave. So what I'd like to see is a second video where you are building the symmetrical diode circuit, put in a sine wave, turn your volume up and down, and take a video. Explain to me what is happening and how it relates to what you saw in the DC circuit in part 2. If you could, try to identify the voltage that you're seeing the flat line. You can use the divisions on your oscilloscope. You should be able to tell me roughly where the flat line is happening. So that's it. That's all distortion is, right? We are chopping a signal after a certain point so that we are kind of just isolating the wave at a certain point, and what I did was I amplified it first so that I had a much larger wave going in, so the distortion was much more clear when we listened to it with music. So let's now see if we can do some other practical applications. Distortion is one of these effects that I think works best in like a guitar pedal chain. Although you could distort music like I was doing, you could distort your vocals. There's a lot of things we could apply this to. But since this is most related to guitar, I'm going to get into a couple different things that are guitar related for today that we can do. So, basically, okay, small explanation. This is essentially what all distortion is, what it looks like. Every distortion pedal, analog or digital, will behave like this. The differences between distortions being different clipping curves of devices that cause distortion. So you can use transistors, vacuum tubes, voltage-controlled amplifiers, op-amps, etc. to create distortion. And other tone sculpting techniques like putting filters on the inputs and outputs, chaining multiple stages of distortion, and doing more sophisticated variations that can distort the plus and halves of the waves. You can imagine if I were to take the output of that distortion, run it through another gain stage and another distortion, I can kind of cascade this effect to make things more and more distorted. And so there are lots of different ways to sculpt distortion, and there's a lot of guitar pedal companies out there that pretty much use distortion as their entire line of products. So there's a lot you can do with it, and it gets more into how you distort the signal using these different techniques. So if you haven't already, please explain to me what distortion is. Explain it like you explained breadboards and multimeters earlier in the semester. So, now that we've done that, let's do some fun things. I want to add a crossfader. Basically, you know, I have this distortion, and now I want to fade between the input and the output. And basically, this is your common wet-dry mix that you have on a guitar pedal, right? Where your wet side of the knob is your completely distorted signal, and your dry side of the knob is your completely clean signal. And so we're just going to use a simple pot to do this. We're going to use the little blue potentiometer. And I'm going to keep this amplifier on here just so I can hear it. You can do this with just the sine wave and the oscilloscope, but I think it's more fun to use it with music. So let's grab this little potentiometer here. And basically, my signal is going to be coming out of the center of this pot. So I'm just going to stick my yellow output cable there. And I just have two places, right? Here's my distortion where my diodes are plugged in. I'm going to put that on one side of this pot. And my clean signal is pretty much where my audio is coming in. Now I'm going to pull this from pin 3 of my amp because that's where I'm going into the gain stage. And so let's hear this with a crossfader. Clean. Now we can do this with the sine wave too. I'm going to just unplug this from my audio because I don't want to listen to the sine wave. But we can look at what this looks like using my sine wave here. So as I turn this pot, that's my fully distorted signal, and I'll watch it slowly. Oh, you know what? I left this here. I should probably look at the actual output of the potentiometer. There we go. So yeah, basically distorted, clean. See how much the gain went up after that gain stage. So this is how much voltage I'm actually chopping off by doing this. So, build yourself a crossfader. Show me, again, you don't have to build the amplifier and use music, but if you show me a video using the sine wave, so I can see it go from clean to distorted, this is a pretty useful circuit. You know, it's just, you have a clean signal on the left side, you have a distorted signal on the other side, and you're able to kind of crossfade between them. Now this applies to a lot more things. If you're using filters, if you're using two different oscillators, you can crossfade between a lot of different circuits. So while I'm using this as a wet-dry mix, you can build a crossfader that, you know, also goes between two different kinds of signals. So make a crossfader. Take a video of your scope as you fade it from completely clean to completely distorted, and explain what's going on. How about a bypass switch? This is another common guitar feature, right? Sometimes we want to not use our effect pedal at all. We would just like our clean signal to pass completely through so we can hear the clean signal, and we flip it on, we can hear the distorted signal. So I'm going to leave my wet-dry mix in because that's part of my pedal, right? I would love the idea of being able to, turn this from wet to dry. But when I hit my bypass switch, I'm just going to send my clean signal completely over my entire effects chain. So I'm not going to draw this circuit, but I would like you to draw this circuit and build it. And I would like to see the scope with the bypass switch turning it on and off. And when it's on, I should see the actual crossfader working. So I'm not going to actually build this one, but I'm just going to give you some tips on how to do it because I think you're all capable of doing it yourselves. My bypass switch is switched between two places, right? I should be able to, I'm going to put it on my output, right? So down here, this is the end of my wet-dry signal, right? So this is my effects output. My clean output is actually like way up here before I even hit the op-amp, right? This is coming out of my DC blocking circuit. So this is actually, I'm going to unplug it for a second. This is the other side of my switch, right? So I'm going to leave this here because I want to keep this in pin 3. But basically, I would like to be able to crossfade between my totally clean signal up here and my distorted signal with my crossfader on the other side. The middle of my switch is then going out to my scope. So I should be able to look at either side of the switch as I flip it, right? And so I want you to try and build that and draw a schematic. See if you can get it working, okay? The crossfader and the bypass switch are, a few of a lot of different things that you can do with guitar pedals. And I think next week I'm going to actually do a special video about guitar pedals specifically. It won't have an assignment to go with it, but it will be the video for Lab 10. So I'm going to get into knobs, I'm going to get into enclosures, I'm going to get into different ways that you can make, a guitar pedal that's useful that you can tour with. So for those of you that are going that route, week 10 is going to be useful for that. So there's a couple other things that I'm going to ask now, and these are sort of questions that I want you to answer. And these are pretty common sense, so don't think too much about them. But let's say you want to plug your guitar straight into this thing and use it. The signal from your guitar is way too quiet. So what simple-ish circuit do you have to add to the circuit that you just built? I'm not going to answer this, but I'll let you answer it for homework. The circuit with your laptop audio input isn't that distorted because of the limited amplitude of the signal coming out of your computer. Say you want your signal to be more distorted. What simple-ish circuit do you have to add at the beginning? Hint, it's the same thing as 6A. Second hint, I built it. Right? We listened to that circuit when we did not hear distortion. So I was forced to build this circuit so that we could actually hear the distortion. Third question. The output of this circuit will have some high resistance that could interact in some annoying way with the input of the next pedal. So what simple op-amp circuit that we've built before could you add to the output of this to eliminate this problem? This is not the same as the previous questions, but you should be able to answer this based on what we've done in the past. So you're going to answer those 3 questions, and then I want you to answer these final project questions. So some of these you may have answered already, and you may feel like you're answering them again, but I just want you to kind of keep narrowing down, keep focusing on what you will be building. This is the last lab that has an assignment associated with it. So you're going to explain in a few paragraphs what your final project is, include the flow of the circuit and what it does. So I didn't actually ask you to do this last week, but I would like you to do this week. I want you to make a block diagram of your final project. I want you to show me the path of the signal. What it starts, is it coming from your guitar, from your laptop, is it coming from an oscillator? Where does that go? What happens next? You know, you don't have to draw the schematic just yet, but I want you to draw blocks and arrows showing me how your signal travels through your final project. Second part, draw a diagram of the actual interface it will have. What are the inputs and outputs? I want you to tell me kind of how I'm going to be playing this thing, hypothetically, if we were in person. What buttons are there, what sensors, what knobs. You may have done this last week already. You can send that if you already did it. Third part, start buying or ordering parts. If you need assistance, please ask. Ideally, you should have your parts in the next week or two. I've been talking to everyone in office hours about final projects, so I want you to start buying the things that we talk about. This week, we are really sitting down and talking about your final. So by the end of your office hours, you should have a plan on what you need to get. Let me just go over this lab once more before I get more into finals. So basically, you're going to build some distortion circuits. You're going to measure your diode. I want to see the 3 measurements of voltage that you get using 3 different resistors. You're going to build your asymmetrical clipping circuit, and I'd love to see a video of a sine wave as you clip it. You're going to build your symmetrical clipping circuit, and I want to see a video of the oscilloscope with, you know, the sine wave getting chopped on both sides. You're going to add a crossfader, and I'd love to see a video of you turning the wave to go from wet to dry. And then you're going to add a bypass switch. And I'd like to see a schematic of this plus a video of it working. You're going to answer these 3 questions about clipping circuits, and then you're going to answer these final project questions. So, now that we've gone through all this, what I want to do is just go back to analog lab, right? So basically, this is the landing page for the site. As we get into the last few weeks, I'm going to do informational videos on each of these weeks. Guitar pedal design will be next week. 555 timers will be the week after that. I'll have a couple others. These will not have assignments associated with them. These will just be for your, information. You should watch them because there might be useful stuff in there for your final, but some things might not be applicable, right? If you are building a oscillator circuit, you might not find the guitar pedal design helpful. That's okay. The other thing I want to look at here is the syllabus. So basically, every week you have an assignment that is out of 5 points, and this will not change. We are going to have blog posts due every week of finals. However, starting next week, your final project reports are just telling me what progress you made on your final. As these progress reports get deeper, we're going to have more information. I would love to see a video. I would love to see schematics and diagrams. Basically, I want to see each week that you are making progress. Your progress reports are graded out of 5. Please turn them in on time. Please do them. I've had straight A students that stopped doing their labs during final projects and lost a whole letter grade because they stopped doing final project reports. So I am grading these. I want to see that you're making progress each week. I may not have them on here. I think they're on last year's syllabus, but I will post them next week so that, well, let's see. Let's see if they're on last year's. This is what I wanted to see. Okay, so final project schedule. So I just want to go over these really quickly. Obviously this is applicable to an in-person class, so this is, maybe a little different. This is going to be a report on your project so far, include a description of what you've accomplished with photos, videos, and schematics, and a checklist of everything left to do. I think it's a good idea to have a checklist each week so you know what you have to accomplish week to week. This report counts the same as your other lab reports and must be handed in on time for credit. The written section should be thorough and a few paragraphs long, and it should contain a list of everything left to do. Lab Report 11, this is 2 weeks from now. Report on your progress so far. Your project should be about half done and should have multiple functioning stages. Include a description of what you've accomplished, photo, video, and schematics, and a checklist. Then week 3, Lab Report 12. I want to see a 30 to 60 second video of your project working. And then in week 4, your projects should be finished and functioning. Basically what we said was the second to last class, the projects were due so that you have a full week to work on your final project report. And then your last week, what I think we're going to do is do a big Zoom class together where everyone can present their final projects. And we'll probably just do that during our normal class time, so 9 a.m. on Monday or Friday, depending on which class you're in. But I'd love for you to demo your final projects for all the other students, and you can get a chance to see what everybody's working on. So we'll keep it quick. We'll keep the presentations like just to a demo and a couple questions, but I would like for the last week of class for you to present your final to everyone over Zoom so that we can kind of share them with everyone. So that's what the schedule is going to be like. These are 5 weeks that we have solely dedicated to final projects, so you should be able to get something working in this time. I will be meeting everyone one-on-one, so we should be able to kind of work out any bugs that you're going to have in the meantime. So, with that, that's the end of this lab. Feel free to email me with any questions in the meantime, and I'll see you in office hours this week.